Okay, let's start. It's really my pleasure to welcome Dr. Raedt. He's a full professor at the Department of Computer Science at TU Leuven and director of Leuven AI, which is his new institute that you have there, which is fantastic. He is also a guest professor at Forever, linked to the Wallenberg Foundation of the Wallenberg AI, which I think is very prestigious and it's amazing. He received his PhD from TU Leuven and was professor of machine learning and chaired machine learning at Freiburg in Germany. And his area of research is AI, machine learning, data mining, and we know we all know from his contributions in these areas of learning and reasoning, and in particular nowadays, where the need for this combination of machine learning with symbolic AI is so important. I really welcome He's also been chair of many important conferences, namely the EPIA this year in 2022, and is a Neuro-AI fellow, a EPIA fellow, a EPIA trustee, and had an ERC grant in 2015. And I'm so looking forward to your talk. Thanks for being here.
Thanks for the wonderful introduction. Thanks for the kind invite. It's very good to see a vibrant Portuguese AI association with community and conference here. So it's my pleasure to talk about this learning and reasoning, where I'm going to combine different paradigms, logic, probability, and since recently also neural networks. And this is, of course, joint work with a whole team. And the most important people you see there, like Robin, Angelica, Giuseppe, Sebastian, Thomas, and Thomas. Okay, the first observation that I'd like to make is that learning and reasoning are really both needed in AI, and there's various indications of that. If you look at the literature, it's kind of common to see this book by Daniel Kahneman, who talks about system 1, system 2, thinking fast and thinking slow. And these are like two different things, because in thinking fast, you look like at an image like that and you directly recognize, Anna, I don't have to think about that. It's clear. But if you think with system 2, then you have to take a couple of steps. You have to reason, like planning to be in Portugal at this conference involves several steps. And so you need both this learning and this reasoning. Now, this dichotomy of system 1 and system 2 is like known in many different terms. People talk about the data-driven, the machine learning approach. Like you can learn from a lot of images to recognize people. And then, okay, once you've got your classifier, you don't really have to think about it. And that's like thinking fast. Then there is the sub-symbolic versus symbolic divide. There is solvers and learners, as Hector Geffner likes to call it. And then there is neurosymbolic versus symbolic, or good old-fashioned AI. Now, the arguments come from different perspectives, actually. I mean, there's Daniel Kahneman from cognitive science. There's people like Gary Marcus. There is people coming from logics, like Adnan Darwish, like Levesque. But there's also like people in neural networks, like Jan LeCun and Sami Banjo. They actually also argue that you need learning and reasoning, that you basically need the best of both worlds. What people do not agree about is how to combine learning and reasoning. And I'm going to give you one perspective as to how to do that. You can also look at it from a more practical perspective. I mean, if we we learn how to drive. We have to pass a driver's license test, and this is the kind of questions that we get there. And if you look at this test, there is like both aspects. The system 1, system 2 are both involved. You have to recognize, where the cars are. You have to recognize where the pedestrians, the traffic signs are. And this is very much like at the sub-symbolic level, the level that neural networks excel at. But then also you want to reason about that, because you need to reason about the rules of traffic to see who can go first. And that's something you don't want to learn with neural networks. So you need this thinking fast, thinking slow. And the main paradigm for thinking fast is, of course, neural networks. And the focus is very much there on learning. It's amazingly efficient at solving perception tasks that we couldn't dream of like even a decade ago. I mean, it's so efficient there. But what is sometimes forgotten is that there's also a lot of progress in thinking slow, in reasoning. And in particular, the two main paradigms within the field of AI are logic and probability. And there's also been a lot of work over the past 20 years or so in combining this logic and probability in fields known as statistical relational AI, in probabilistic programming. What's also kind of interesting is that they've been combined. They've also been used as representations for machine learning. If you look at the book of Pedro Domingos, the master algorithm, which describes the quest for the ultimate learning algorithm, then he talks about 5 different schools. And 3 of them are this logic, probability, and neural networks. And that's kind of what we try to combine, logic and probability, because they also look at reasoning, and then neural networks because they're so good at perception. And that's in a sense related to neurosymbolic AI and neurosymbolic computation. Now, neurosymbolic computation is actually often viewed as combining these logical representations with neural networks. The key message that I want to convey here is that we can take a lot of information from this field of combining probability and logic, and that actually will carry over to neurosymbolic AI. The reason is that many of the problems that these probabilistic logics have, if you want to use these for learning, if you want to use these for reasoning, that they come back if you want to combine logic and neural networks. And that's going to be part 1 of the talk. That's actually also the basis of a survey, and we gave tutorials about that at AAAI and HCAI that you certainly can find on the web. I must say that this does not cover all the meanings of the term neurosymbolic. I mean, some people say, well, the symbols are words, and you can reason with that. And of course, that's also true, but that's like not the kind of perspective that I'm going to take. I'm going to focus on more this formal representation, this logic and probability as neurosymbolic computation. Now, if you look at most of the neurosymbolic approaches today, what they will do is they take logic, they use that to express some knowledge, some kind of rules, and they then inject that into the neural network. And once that's done, they forget about the logic and suppose that the neural network will take over and will do everything. The downside of this is that a lot of the typical reasoning and inspection and explanations that you can get with these traditional representations, that they're kind of lost because they're inside this black box, this neural networks. And that's why we propose a different approach. And the feeling is there that if you combine like 2 or 3 different representations, and you say, I'm going to unify these representations, then you want that the unified representation has all the abilities of the original representations. If you say, I'm going to combine logic, probability, and neural networks, well, then you basically want to have special cases that are logic, probability, and neural networks, that you retain the same abilities and more. And in this way, 1 + 1 becomes 3 in a sense, right? Or 1 + 1 + 1 should become 4. You should be able to do more with these extended representations. And I'm going to give you some idea of what we're trying to do there. I'm going to use our deep Problog system and our related system, deep Stocklog, to kind of illustrate that. So there's two parts in the talk. In the first, I'll go from this probabilistic logics to neural logics, and I'm going to argue that they have a lot in common. Actually, in the paper and the survey, we go along 7 different dimensions and really argue that these have a lot in common. What I'm going to do today is focus on 1 or 2 of the key things that they really have in common. And one of them is really that there's 2 basic types of logic, graphical models, and neurosymbolic methods. I mean, if you look at logic and graphical models, then you can reason about directed, you can reason about building proofs and stuff like that, or you can reason about undirected, and then you take a model-based approach, and that comes back in this neurosymbolic methods. So this is like logic programs, the very simple case. I'm not gonna go into a lot of depths about these logic programs, but what you have there is a couple of facts, like burglary holds, Mary hears the alarm, and these are all facts that are supposed to be true. Then the second thing is that there is rules, and these rules say that, okay, if the alarm goes off and Mary hears the alarm, then Mary will also call. So these are just like if-then rules that, of course, you can also execute, and you can give meaning to within the logic programming formalism. This is just like simple Prolog. Once you have that, you can do 2 things. On the one hand, you can build proofs, and that's what we do here. Here on the right hand, we have like this proof tree where you want to show that Mary calls, and then you can use these rules to kind of infer that. I mean, Mary will call if the alarm goes off and if she hears the alarm. And so that's like the first step in this tree. And then you can look at alarm. There's 2 possibilities for that, if there's an earthquake or if there's a burglary. And so you have 2 alternative proofs. And then these proofs kind of develop until you're at the bottom of the tree and your proof is kind of finished. So you have like 2 successful proofs here. And that's like one perspective, a proof theoretic perspective. The other perspective is more like the satisfiability perspective. There you say, well, I got these rules, but these rules, they act as kind of constraints. Whenever, one part of this equivalence is true, then the other part should also be true. And that gives you models, kind of possible walls, things that are possible because they satisfy your rules. It's very much like SAT solvers, right? It's that kind of perspective that we have. And you see, for instance, on the right-hand side, you see one such possible walls containing just the facts that are true. All the other facts are false. And you can see that all of the rules here are satisfied. For instance, you see that alarm is true, John hears the alarm, and you see that also the other part of the second rule, John calls, is part of that. And that's just a model theoretic perspective. Now, that's logic. Let's go to probabilistic graphical models and to neurosymbolic systems. And there also you have like this kind of distinction. On the one hand, in graphical models, you have the directed versus the undirected ones. And you have like Bayesian networks. This is the traditional famous Judea-Pearl example of alarm. And on the right hand, you have like an undirected one. And in the star AI systems, there's also like 2 versions of this. One is like this probabilistic prologues, like the one that we built. And on the other hand, you also have like this Markov logic, which acts as kind of soft constraint. And so you have like 2 different representations. What's kind of cool is that you also find back this distinction within neurosymbolic systems, where on the one hand, you can use logic to kind of, as a kind of neural program. I mean, the proofs become, in a sense, the structure of the neural network. And on the other hand, you can use constraints as a kind of regularizer to make your neural network obey the constraints that are given. And let me illustrate that. One of the very earliest approaches in neurosymbolic AI is K-band. That goes back almost 30 years to Towel and Chuchavlik. And what they were doing is, well, they were starting with this kind of propositional rules, very much in the style of this Prolog example that I was showing earlier. And they would then kind of rewrite these rules a little, and they would turn that into a kind of and/or tree. And that and/or tree is very much like this proof tree. In a sense, it's a summary of the possible proofs that you can get. And that's what you see on the right hand there. They would then use that as a kind of neural network. I mean, the input layer would be the elements at the bottom, and they would then try to predict what's at the output layer, but they would not do so before making some changes to the structure. I mean, in the spirit of neural networks, they would add some hidden nodes, they would add additional links, and yeah, they would also add some spurious ones, and yeah, then they would start training. And that was like probably the earliest neurosymbolic system, where you have logical rules built into the neural networks, and then the neural network was training in a sense. And that's very much, yeah, this first type of approach. It's a proof theoretic approach. And you can see that this old way of doing things, it actually comes back in a lot of the recent systems. Here you see like lifted relational neural networks, which does exactly the same kind of thing. They would also build proof trees. The proof trees would be turned into neural networks. And then you would do all kinds of operations on that. There's a very fancy system, one that I like a lot, that also was doing cool stuff with knowledge bases and knowledge graphs. The neural theorem prover by Sebastian Riedel and Tim Rock-Teschel. And they would also like use rules. Well, you see on the top right and the top left in the figure, you see some kind of Prolog rules, and they would then use that again to build proofs. But they had one interesting modification, and the interesting modification is that they would allow for soft matching. I mean, for instance, if you have like the predicate grandfather, which should succeed if X is the grandfather of Y, then they would also use kind of embeddings to do kind of soft unification. So they would allow grandfather to also match with grandpa, which makes of course sense because, well, they probably close an embedding space, and so they would build this trees in a sense with soft unification principles. The downside of these approaches is that, you know, both of these approaches, or all three of these approaches, they take the logic, they convert that in the neural network, and then it's up to the neural network to kind of learn. And the logic is, in a sense, encoded in the neural network, and it's kind of forgotten. And so afterwards, it becomes very hard to reason in the pure logical way. Another system that belongs to more this kind of SAT solver category is to use really logic as a kind of soft constraints, as a kind of regularizer. And if the constraints are not satisfied, you're going to penalize the neural network in your loss function. And a clean example of that is the approach by Xu et al. In the group of Guy van den Broek, where, you know, logical constraints are used to regularize the neural network. And the example they give is this one. You have a standard neural network, and the task is to do multi-class predictions. There's 3 classes. You have 3 output nodes, and each of these output nodes will get a particular value. And if you don't use anything special, well, the values can go like 0.1, 0.8, 0.3, 0.9. And that's probably not what you want, because, well, only one of these should have high values, right? You're doing like multi-class classification, so only one should have a good value. And therefore, they impose constraints. Constraints like here that says, well, there should be at most one of the outputs that fire. And that's written down in propositional logic. And they would then compute the probability that for the values that you have, this 0.8, 0.3, 0.9, well, they would compute the probability that the constraint is satisfied using these outputted beliefs in a sense, and they would use that to regularize the neural network in what they call semantic loss. Semantic loss has very nice properties. If you want to see more about that, I would say have a look at their ICML paper and some follow-up work on that. But what's important here is that you can kind of use these constraints to regularize, to steer your neural network in particular directions. Again, that approach is very fashionable. It's the purest approach is probably the semantic loss. But there's been other variations like work by Serafini, Gasset, who do very similar things. They would, take a kind of constraints and use that as regularizers. Also, semantic-based regularization by the Siena group is working on that kind of approach. But again, you see that once the logic is kind of used to regularize, well, again, everything is encoded in the neural network, and so the ability to reason is in a sense disappearing. It's just used to force the neural network in particular directions. And so that's well, one of the first lessons that Starry and Neuro-Symbolic, they kind of pretty similar. I mean, you have like one of these dimensions which says you have directed versus undirected, proof versus model theoretic, or this, probabilistic programs to determine the structure of your neural network, or you have like this constraints to regularize. There's a lot of other things to say. I mean, just like in Starry, you can choose what the numbers mean. And there's at least 3 different possibilities in Neuro-Symbolic. You can say, I'm going to go for the pure logic, that's a 0-1 or a true-false distinction. And some people, like the group in Nanjing around Ziwa, Zhu has done that. The difficulty there is that it's hard to optimize. You can go for a probabilistic interpretation, which is what we do and what also like the semantic loss do. And then you can go for the fuzzy approach. And in fuzzy, the weights, they don't really capture probabilities. And there's a lot of work around that. In the semantic loss, for instance, you see that you can, if you have this constraints, and you have these weights on the formulas, that you can give probabilities to possible walls, and that's like one approach. In probabilistic logics, there's also like Markov logic that is quite fashionable, and the derived PSL that I'll go to in a minute. And what they do is, rather than associating probabilities to these facts, they associate probabilities or weights to rules. And then the intuition is that the higher the weight, the stronger it should act as a constraint. And ultimately, if the weight is infinity, then it's a hard constraint. And so with this, you can again give more or less weight, more or less belief, more or less probability to these possible worlds. It's a quite different framework, but that framework has then been expanded by the group around Couture. And what they do is they have these weights on these formulas in very much the same spirit as for Markov logic, but they would again also have like possible walls that would have a kind of membership function. Like burglary would, it would be 0.7. It's 0.7 of a burglary. And that wouldn't indicate the probability, but it would indicate the membership function. The reason why they are doing this is that fuzzy and this kind of way of doing things is a lot more computationally tractable than the probabilistic interpretation. Probabilistic inference is hard. But this PSL and the approaches on fuzzy are a lot more tractable, and that's why people resort a lot to the fuzzy interpretations. The downside, however, is that a lot of the intuitions that you have about logic, like if A implies B and B implies C, well, you would also expect that A implies C, and that is not always the case for these fuzzy frameworks, and that's why you get some confusion there. Again, this logic as constraints is used in others, like logic tensor networks, where they use fuzzy, semantic-based regularization, where they also use a fuzzy interpretation. And again, there are some consequences of that. So and that's why we go actually for the probabilistic version and the probabilistic inference. And so the key message there is that, well, if you combine logic and probability, or logic and neural networks, you should have the originals as a special case. And I've tried to argue that you don't have that with the approaches that I kind of talked about, because the logic is kind of injected in the neural network, or you use this kind of fuzzy interpretation, which also has some downsides. Fuzzy is used for convenience and for mathematical tractability, but not for the clean semantics and the meaning of things. And that's why we propose a different approach. And that approach is kind of getting a kind of interface layer between the different components. It's an interface between the probability, the logic, and the neural network. And I want to stress that interfaces are different than pipelines. Pipelines, I think, are for plumbers. And so interfaces, you have like bidirectional kind of flow of information. In a pipeline, there's only flow in one direction, and that's what a lot of the other systems are doing. And I'm going to illustrate one approach. It's still pretty early, although we are working on this already for quite a long time. But it's based around this probabilistic programming framework called Problog, and that has recently been extended with neural networks. And that's what you see here. I should just watch time. So the deep Problog framework is really retaining the full expressivity of the logics. It's actually a generalization of the Prolog programming language. So it's a programming language. It also can simulate Bayesian networks, graphical models, and it has a pretty clear semantics, unlike some of the related work in neuro-symbolic approaches. And so in the second part, I want to briefly go from logic to probabilistic logics. That's from logic to Problog, and then from Problog to deep Problog, taking that lesson into account. So this is the example that I was giving about logic programs, this burglary example with the proofs. Now we want to make this probabilistic. And it was the seminal insight of Taisuke Sato and David Poole to say, well, if we want to unify logic and probability, the one way of doing that is to take the simplest concepts should kind of unify. And they then also observed that when to operationalize that, what you need to do is you need to take these facts and you make them probabilistic. And what you then get is that the probability of burglary is 10%. And probability of Mary hears the alarm is like 30%. And that's the kind of way of turning Prolog into a probabilistic Prolog. Furthermore, you make the assumption that these probabilistic facts are marginally independent. And then people always ask, well, can't you encode independencies? Dependencies and independencies like in graphical models. And of course, the role of the facts is very much like, you know, the nodes without any ancestors, the node without any parents in a Bayesian network, right? These are also marginally independent. And the rules encode then the dependencies. So that's in a sense all that you need to turn that into a probabilistic logic. And then your proofs are also going to become probabilistic. Here you see the two proofs for alarm. You can take the left branch or the right branch. And to take the probability of a proof, it's easy. You just multiply the probability of the things you've used, the facts you've used along that proof. And then it's very tempting to say, well, I've got two proofs. So the probability of alarm is just going to be the sum of these two proofs. But that's, of course, a mistake, because if you have the probability of A or B, you simply shouldn't add it. You should also subtract the intersection. And that's actually leading to quite some computational problems. I mean, it's computational problems that you also have in graphical models and Bayesian networks. That's intractable. It's well known, but there's still, we can do a lot of cool stuff with that. And there's also been a lot of progress in inference on these matters. You can also view these probabilistic programs as kind of generative models. That's what you see here. You've got like this tree, which is kind of a generative tree of possible walls. Like initially in the top, in the root, you start with the empty possible walls. And then you go through your rules on the left. Earthquake is there with 100% probability. So that's what you get as the sum of the root, so to say. And then if there's an earthquake, that's your third rule. Then there will also be an alarm with probability 60% and no alarm with probability 40%. And so you get this branching in a sense at that stage. And then again, you can look at what holds in for instance, the partial possible walls, you know, that we have here. Right? You can look at that. And again, you can apply the same kind of process until the leaves will give you all the possible walls. And there you can then look at what's the probability of one of these possible walls. Well, it's just the product of everything you got along that path. So for instance, the leftmost pass, you just take the product of that, and that's going to be this 0.6 times 0.5 times 0.8. If you then want to know, like, what's the probability of a query of alarm, for instance, well, you look at those possible walls, the leaves, where alarm belongs to, and you sum up their probabilities, and that's what you're going to get. It's very clear that with this kind of approach, you can do what graphical models do, and in a sense, this Problog and this directed probabilistic programs, they directly generalize Bayesian networks, but you can do much, much more because you've got a programming language, and also because you've got a first order logic representations. And people have, for instance, devised, you know, this plate notation that's quite fashionable to describe graphical models. Here you've got like a standard Bayesian network, but with plate notation. So there's two plates, one for courses, that's the right one for students, that's the left one. And then what this actually means is that if you have students and courses, then you can, in a sense, unroll that network to get that network that you have on the right, and everything becomes connected, so to say. And that's the power of plates. It's the power of working with these variables and these relations, in a sense. And then you can really connect the performance of one student to the performances of the other students, and that's like what these plates allow you to do. In these probabilistic logics, you can do even more. You can also very easily encode ontological knowledge, like for instance, what it means in terms of rules that students do not pass, that they are excellent, that they get some award or whatever. It's very easy to encode that in a kind of logic. And then you can reason with all that afterwards. Just one slide about inference, because here is where all the tricky parts are. The inference goes as follows. You have an example on the left, and then you have a particular query that you want to get the probability for, and that can be, of course, a conditional probability. The first step is that you're going to ground the program with regard to the query. I mean, there's like these two constants, Mary and John, that appear. And we had this one variable X in red at the bottom. And so you can ground out your rules. This is what you get. You can then rewrite your program into a kind of propositional logic formula. And then you can compile that, and that's called knowledge compilation. You can compile that into a circuit. And that is an expensive step. But it's the step that makes learning, inference, and also deep learning work later. You get this and/or circuit, and on this one, you can compute easily because you've got AND and OR nodes, and given the special form of the circuits and the guarantees provided by that representation, you can then replace the AND by multiplication and the OR by addition to compute what you wanted. That's in a nutshell. We've done quite some applications of Problog. We've done long time ago already, like looking into dynamics, into multiplayer online games, like Travian, where you can try to model how the world will evolve over time. And of course, the idea is that if you can build a model that will predict what the world will look like in the next 5 time steps, you can of course take better action. You can do like action and activity recognition with that. You can reason about occluded objects. I mean, there is versions of Problog that work with continuous distributions, not just discrete one. There's also been some work that's actually been in collaboration with the lab of IST here with Jose Santos and Plinio Moreno, who was doing a lot of work with one of my students, where we were actually trying to learn the effects of actions, a kind of probabilistic planning-like representations like this PDDL in a first phase where you would, tap on certain objects and see how much the displacement was and under which situations you could do that. And then you could also reason about how to, well, you could use these learned action descriptions, this PDDL-like representation to then do a bit of planning and see what sequence of action you need to execute to put certain things on a shelf. We've done applications in biology to identify like relevant parts of molecular interaction networks to explain which ones are the most relevant, and that's a bit explainable, trustworthy. If you're interested in Problog, I would invite you to go to our website. There's a very nice tutorial that's going online, and that where you can actually try it out with your own programs. And it's yeah, there's a lot of examples there. But now I also promised to go to Neuro-Symbolic. Nice to check how much time I still have. Very good. And so I already have probability and logic, and let's now look at what it takes to turn that into a neurosymbolic system. And the key thing that we were trying to do is like inspired by Sato and Poole that said, okay, let's try to take simple concepts in logic and probability and unify them. We try to look for something that's simple in a neural network and in logic. And so we came out to, well, let's turn neural networks into predicates. And so we talk about neural predicates. And that concept is also pretty powerful because, well, all what you then need to do is to put these neural predicates into your probabilistic logic system and work as you've always worked. That was a bit the idea, and it's best illustrated conceptually on this MNIST examples, where you indeed have like an MNIST, and the neural network would recognize that as belonging to one of 10 classes of digits. And so you can turn that into a neural predicate that will actually do that. The declarations that you see is like, okay, we're going to introduce this digit predicate. That's going to be the neural predicate. X is going to be the input. That's an MNIST image. Y is going to be the output. That's, one of the 10 digits. And then that's going to be encoded by this yellow thing, this neural network. But what matters is that if you then call digits with an MNIST image, what you get is a probability distribution over the possible outputs, like the probability of 4% that it's a 0, 35, that's a 1, and so on. And that kind of expression you can directly encode in these probabilistic logics. You can directly use that. And so that says nothing else than this digit is one of these 10 classes with these probabilities. And that's like an OR that you have. And that's actually all you need to turn these probabilistic logics into neural neuro-symbolic AI systems. And then you can start play. And the first thing we tried is let's take simple additions. And so we were trying to learn addition. And addition, the examples we were giving was like 2 MNIST images, and then there's some. So 3, 5, 8, where there's 2 digits, 2 MNISTs and 1 result, so to say. And we would also equip it with background knowledge, like how to perform addition if this neural predicate would be perfect, right? And you can see how that works at the bottom. If we take this first positive example of additions 3, 5, 8, and we put that into that rule, then you get like digit 3 becomes N1, digit 5 becomes N2, and 8 is the sum of the 2. And so what this is actually enforcing is that there is kind of a constraint that holds between the 2 output values for the 2 different MNIST images. You can get like 1 and 7, you can get 3 and 5, you can get 5 and 3, but you cannot get 2 and 2, because 2 and 2 would not sum up to 8 in a sense. And so this simply encodes constraints in the logic. And then, of course, yeah, we compare it with standard neural networks, with CNNs, and you can show that very easily that it does better. Of course, that's not very impressive because, you know, it's just M2 MNIST images. So let's take something a little bit more fancy. Let's look at these sequences of MNIST images, and let's try to add these together. While neural networks directly apply to the first task, they would have a very, very hard time to do it on this one. And the way that we continued was, well, okay, you just, again, write down what you know about addition. And, you know, there's this neural predicate digit that you don't know, and that's the one that you're actually learning. And, well, if it would be perfect, that's the way to do addition. And you can then show that for the multi-addition, you also get pretty fast convergence to the right kind of thing. And that shows a little bit the power of this. So what you have to keep in mind is that the examples are given at a different level than the neural predicates, right? So of course, learning neural predicates directly would be extremely simple, but that's not what we do. We give examples at the multi-addition level, and then that's automatically translated to examples for the neural predicates. The way that this works is thanks to the circuits. And that was also the cool thing. We didn't have to change much in our architecture because Problog was compiling to circuits. And the only effect that we now have is that these neural predicates, these are like the leaves of these circuits. So digit is, in a sense, in this example, the only neural predicate. And so these leaves, they become neural networks. And what you then do is you get your example at the level of addition, the top level. And then, you know, you just push it down, computing gradients, you push it down to the leaves, and then you push it down further into the neural networks. And so you can learn both the weights of the neural network and the probabilistic parameters of these programs directly. We did do a couple of experiments. We were looking at learning rules with this, and one way of learning rules, the way of learning rules with neuro-symbolic systems, is to work with a bit of templates and to fill out like what are their possible values. And that's a bit similar to other work by the group of Sebastian Riedel and Roch Teschel, where you can look at, for instance, learning to sort, learning more complicated additions, word algebra problems that you can all try to learn with this. Here you see like a sorting example. And the thing that is not known here is when X is smaller than Y, and that's the thing that is being learned here. So you give like everything except the X less than Y, and then you give examples of sorted and unsorted lists, and you basically learn that. And okay, you could see that we're faster and better than the other approaches. To illustrate noisy addition, and the learning of parameters, probabilistic parameters. Here you see like a noisy version where, you know, with high probability, you do the correct addition, but with a probability noisy, you output a random value. And then what you can see is that with the learning of the Problog, you can actually also recover the fraction of noise that you have in there. And so you can learn both the neural and the parameters of this. We've done stuff on poker, trying to predict the probability of winning games. We've done things on some simple NLP tasks, on word algebra problems. And now we're looking at kind of scaling this up to be able to do the things we did here with together with IST, but to do it fully kind of neuro-symbolic and probabilistic, because there was still a lot of pipelining in the loop here. Maybe also just indicating how this unification, the soft unification works. I said at the start of the talk that there is a grandfather of that would automatically be mapped with something like grandpa of, and soft unification can be simulated in this kind of approach. You can actually also work with the embeddings inside the logic and exchange information. And that's why it's really an interface. One of the examples that we did there is with a kind of soft equality, where you would embed these M-lists and then make it soft by taking a radial basis function. And you can then do operations on these with these embeddings. And here you see, for instance, that you can take 3, 5, and the difference between 3 and 5 is 2. And so if you also embed a successor kind of predicate, you can do the operations on the vector and simulate a kind of trans-E with these kind of approaches. What is nice that if you then try to visualize it, if you learn from such examples, you know, successor and 3, 5, 2 and similar, and if you then kind of visualize these where the numbers go, then they all come at the line, you know, about one apart in a sense. The recipe that I've given for neurosymbolic is kind of generalizable, and many people have actually copied the idea of this neural predicates to start from a logic and to make it neurosymbolic. One way of proceeding is to take that logic or rule-based systems, and then you typically have a 0-1 approach, or a fuzzy or a probabilistic interpretation. Well, you can take the 0-1 and you can turn that into, well, either the fuzzy or the probabilistic interpretations. And then what you do is the neural networks, they should just become these predicates. So what you do in these other frameworks, you take, you know, these predicates, these conditions that are in there, and you just turn them into neural predicates. You put the neural network on top of them. So conceptually, it's really very simple to do that. The hard part then is, of course, how to implement it in a reasonable way and how to make it learn. As one proof that this approach works, we've also taken another kind of probabilistic logics, which is much more in the spirit of probabilistic context-free grammars. I mean, people knowing Prolog might recall unification-based grammars, this definite clause grammars kind of thing. And this SLP stochastic logic programs are kind of probabilistic versions of that. And our recent sibling of the Problog is just like here. So here you have like a context-free grammar, and you have parse trees on the right. Then you can go to probabilistic context-free grammars, where, you know, if you look at the rules for non-terminals, they get weights or they get probabilities or parameters, and the sum per non-terminal will be 1. So you see for E, the expression, it's 0.5, 0.5. So that sums up to 1. And then what you can do is you can take these parse trees And yeah, you can compute the probabilities of these parse trees. It's just the product of all the rules that you have applied in that in producing that parse tree. And if you apply one rule multiple times, you have to multiply multiple times. So the probability of this parse tree is as indicated here. These PCFGs have been quite useful. You can, compute the most likely parse. You can look at the probability of generating something and so on. So that's like the standard PCFGs. Next step is definite clause grammars, where these non-terminals get arguments and you can do unification. That's kind of interesting to compute, to not only say, well, it parses or it doesn't parse, but also to find the results. The result is indicated there. I mean, the non-terminals get arguments, and with these you can do certain computations and you can carry out certain operations. And yeah, of course, if you have these definite clause grammars and these probabilistic grammars, you can look at stochastic definite clause grammars. That's very close to stochastic logic programs. And okay, now we have something that's pretty close. It's probabilistic logic. So let's take the non-terminals and the terminals and put some neural predicates in there. And you see here that the bottom, again, the non-terminals, that there you can inject these neural predicates, and you can do very much the same kind of stuff, but with a completely different logic and with a completely different functionality. I mean, the Problog is very much like Bayesian networks in a sense. It's directed graphical model. Deep Stocklog is very much like probabilistic unification-based grammars, but you can also use neural networks in there. There's numerous challenges that remain. I mean, efficiency is an issue, but okay, you can also get around that. There's a lot of work on approximating probabilistic inference. We also have a version of an A*-like algorithm for the Problog. There's like, you can extend it with continuous distributions. We're working on that. You can look at real-life applications, and we're now looking at things in a similar spirit of this planning example, where we really want to look at learning kind of PDDL descriptions with these kind of representation. I should stress this is an excellent area for starting researchers, because it really merges neural networks with learning. And yeah, we always have positions, so if people are interested. Okay, let me come to the conclusions. Okay, I hope I've convinced you that learning and reasoning is both needed. One way to go is to merge these paradigms. And if you merge paradigms, then what you want to have is, of course, that you get the originals as special case. And I've given one example of approaches that do this in this deep Problog, deep Stocklog, where neural predicates serve as an interface layer. And the other thing that I wanted to stress is that you can really borrow a lot from other domains like this starry, this probabilistic logics, and this Neuro-Symbolic are very close in spirit, in a sense. Okay, thank you.
Thank you so much for amazing, inspiring talk. People have questions.
Thank you for the talk. So as far as I understood, you talked about the relationship between logic and probabilistic graphical models. My question is a bit high level. Recently, the field of causality has come along in play. So I was wondering, do you think that some tools from causality can be useful here? Do you think so? Because there's logic rules that you like cause and effect type of rules, and causality especially deal with that. And what are your thoughts on it?
Yes, causality would add another dimension, I think, and another level of complexity. One of my students has started to look at it, but we are nowhere yet. So I think it's quite interesting to see what you can represent there. There's been some, I mean, like this. There's a variation on Problog, kind of extension that's called CP logic, and that you can also like execute with our framework, and they call it causal. And they have like looked a little bit at this use, but more from pure KR perspective, not really from a machine learning perspective. They have looked a little bit into that. Yeah. Yeah.
Thank you for the talk. So the biggest motivation that I got to was that some tasks, of course, are easier to do if you have some sort of logical capacity, more than just be able to learn big networks and so on. But if I were to motivate more logical methods, I would maybe clearly say that they are more interpretable.
Yes.
So I wanted to ask why didn't you say that they are
yes
they are necessarily more interpretable?
Yes, I agree. So the logic is definitely, and the probabilistic logic gives you framework. I mean, people talk a lot about interpretability, about trustworthiness, but okay, with these logics and also with the probability, you get kind of standard explanations. You can trust it more, I think. You get it for free. And okay, I should have talked about that. I think the key question is like the key overall question is how to put knowledge inside these AI systems and to combine it with the learning. I mean, to me, that's like where this should be going. That's what everybody wants to do to kind of enhance the effectiveness of today's machine learning systems by putting the knowledge that we have inside it. And yeah, putting the knowledge inside it and being able to reason with it will make it more trustworthy, but it will also compensate for loads of data. I mean, like the example with traffic, with learning, like when to do what, when is it allowed to do what. Of course, you could say, well, a neural network can learn it if it has zillions of data, and probably that's true, but it's kind of stupid, right? We don't learn in that way. And there are rules of traffic. So the question is like how to be able to use that, incorporate that into the learning in a sense. And probably now this is like, yeah, two separate steps, right? But ultimately you would like to see that integrated, I think. Yeah.
Thanks for the talk. My name is Neuro-Symbolic, and I'm an NLP instructor. I was very pleased to see the examples you've given from some colleagues in NLP. However, my impression is there were concerns kind of very narrow domains in natural language. And always, when these approaches are discussed, there's the issue of first how to build a robust representation, because in NLP we are very much focused on open discourse and not on small, narrow problem domains. And there's also the issue of computational scalability of these methods. I was wondering, what are your thoughts on these issues?
Yeah, I think there's still a lot to do in bridging the gap between, I think, the NLP parts and like this kind of approaches. Because this is with formal representations. With NLP, it's all with embeddings and related. Mostly, and there's wonderful work in the NLP community. I mean, like I also listen to these talks of Ye Choi, for instance, who talks about Neuro-Symbolic, but in a quite different, in a different way. Yeah, where the reasoning is all inside this neural network, but it's what I think you don't see so much in contemporary NLP, and please correct me if my hypothesis is wrong. is ways where you enter, you kind of start with knowledge and you use it. It's basically, can I discover everything from the data? That seems to be the main paradigm. But the fact of using existing knowledge seems less prominent. Yes. Yes.
Because the knowledge is very incomplete, and if you want
Yes.
to process undescriptive discourse,
Yes.
you have bad coverage.
Knowledge is incomplete, but it's not right, I think, to say there's no knowledge. There is knowledge. We all have knowledge about, and I think the goal is really, if there is knowledge, we should be able to use it. And we're not. And maybe for English, it doesn't matter so much because there's so much around. But if you look at smaller languages, yeah, there's often, and in specific context, there can be knowledge around. Yeah, it should compensate for data, but at least that's the feeling I have. Yeah. Yeah. Yes.
Thank you for your enlightening talk. This is just a general comment, and I would like you to give your opinion on that very quickly. I would say that combining this topic of combining logic, some kind of logic, with neural networks is not just one more topic in the fringes of the AI area. In my opinion, it's crucial and it may be really important to prevent a black box based AI systems to be banned from being used for at least relevant applications due to lack of transparency and explainability. So this is very important topic for the future of AI. Do you agree with that?
Of course, I agree. Thanks for the comment. I mean, maybe I can add something to that. Like, what you also see is like that there is interesting, and some of them are quite successful approaches in that try to simulate logical reasoning and work for certain problems, like, you know, for a satisfiability or for some constraint solvers. But they don't have the same functionality. They typically work differently, and yeah, and I think indeed, if there's good methods that exist, I think, well, it's a shame to kind of throw them away, and it's rather like adapting them to the new framework. I think that should be done. But I agree. I could not agree more. Thanks.
I think we're
Okay.
stop here. I think this was wonderful, and thank you so much.
Thanks.
Okay, we have lunch now.
Okay, thanks. Yeah, I don't know.